Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is as far from land as possible. So let's go to LeetCode and give this problem a read. Given an n cross n grid containing only values zeros and ones, where 0 represents water and 1 represents land. Typical grid problem, graph problem. Find a water cell such that its distance to the nearest land cell is maximized and return the distance. So if no land or water exist in the grid, then return -1. So either it's all land or it's like all water, or maybe there is no land, there is no water, so something like that. Then we have to return basically -1. Now the distance used in this problem is the Manhattan distance. The distance between two cells is basically it's the same regular distance calculation. So now let's consider first example. Alright, so I have taken the first example here. So this grid has zeros and ones, right? So we don't have to worry about returning -1. So our objective is to find a water cells. What are the water cells? These are the water cells. So this one right here, so this is a water cell, this is a water cell, and this is a water cell, and there is one more. So these are the water cells. Now what we want to do is we want to find, okay, there is one more, I just missed this one as well. So there are 5 water cells, and from these water cells we want to find that water cell, and we're not even returning the water cell, we're returning the maximum distance to the land, to the nearest land. Okay, so what does that mean? So let's say, for example, we pick this water cell and this water cell. So what are the nearest land to this in respect to this particular water cell? So there is one right here, there is one right here, and you can say there is maybe one right here. But this is like 1, 2, 3 distance away, and this is just 1 distance away. Okay, so this zero's distance to the nearest one is 1, right? This is 1. So let's get rid of this. And the distance of this zero, this one right here, to the nearest one would be going this way sideways and then up, so this would be 2. Okay, so this would be 2, and for this 0 it's 1, this 0 it's 1, and this 0 is also 1. So which water cell has the closest distance, closest land distance, and we have to maximize it. So that is this 2. So basically this cell right here, this would be our answer. This cell right here would be our answer. So let's get rid of this. This right here, this will give us our answer, and that answer would be 2. All right, so there are we know it would be the BFS that will provide us the solution, because we will push all these 0 cells into my queue, and then from there I will basically run BFS, so that when I come across basically the furthest land, that's when I will return that distance, basically the level, right? So but there is another way to it, which will really simplify things for us. That is, instead of basically running BFS from these zeros, which kind of basically stops, like when you're thinking logically, like we are trying to find zeros running our BFS from these cells. So let's say choosing this cell, and once you come across this one, then you stop. But then what we really want is we want to find the furthest zero from those ones. So how about we try to find the land, we try to find the water from land actually. So how about I actually run my BFS from these land cells. There are 4 land cells, and I will put all of them into my queue. So 0 1 2 0 1 2, I will have my queue and I will push all these. So 0 0 and then 0 2, then 2 0 and then 2 2. So all of these right here, these are the land cells, and I'm trying to basically have my level or distance calculated. Initially we can assign it 0. I will increment it so that I can keep going and increment my distance until I no longer find a water body. So what does that mean is from this land cell on first level, basically when you're processing all its neighbors, so you'll process this one, this 0, then you'll process this 0, but that's not where you stop actually. Where you stop, from this right here, you will explore this 0, and from this 0 you will explore this 0. So here the distance is 1 to these cells, so this is basically one level. This is one level if you're going level by level, and then there is another level where only this one is present, so this 0, and you want the furthest water body from the land so that you can maximize the distance from any water body to the nearest land. So that is why keeping running the BFS on land and still keep the BFS going so that you can reach the furthest water body from any land. So that's what we will try. We will run our BFS. The solution would be quite simple. This is going to be a simple BFS, but instead of running the BFS from water body, we are running from the land and trying to find the furthest water point. So otherwise, we have done so many BFS problems, so it will be the exact same code. Then you can have the visited set, where after basically visiting these first of all these land, you're gonna mark them visited. But then once you're done visiting these water bodies, also you will mark them visited and increment the distance. So I'm not going to write the pseudocode, right? Let's just directly jump into the code right here. It will be simple. All right. So as I said, let's get the dimensions of the grid, R and C. So length grid and then length grid 0, although it's going to be same row and column, but still. Visited is going to be the set. Now let's add, there is one more thing that we have to do is sometimes it might happen that either the grid has all zeros and all ones, or there are no there are no land and water combinations. So let's say we're gonna say has water initially false, and then we're gonna have has land initially false, and we'll mark them true if we find land and water. So for R in range R and for C in range column, if this grid here R and C is actually equals to land 1, then we want to append it to my queue. So let's have a queue right here, so I'll just call it dq, dq, or maybe I will just have the simple queue. It's much easier for me. I've always found just having that row data structure. But yeah, of course, for time complexity, using those constant time operation, definitely have dq. So queue.append, let's append it as a pair of indexes, and then mark it visited actually also. Visited.add, and then we're marking this R and C as pair visited. Now we have seen land, so make the has land true, mark it true. Otherwise you will see water, and then mark water true. So has water true. Now if not has water, if this is basically false, or this is false, not has land, then you can return basically -1. That was the ask of the problem. Otherwise, let's just calculate the distance. Let's just calculate the distance. So distance initially would be 0, right? Or yeah, initially it should be 0, and then let's run our while q. So here I will just transfer all the values of q to q, and then empty the q so that I can append the next level values. So for, I would say, node in q, for node in q, let's get the R and C of the node, and for dr and dc, so 4 directionally traverse in these pairs, so 1 0. Of course, by now, like, you'll be very comfortable doing the directions, going in 4 directions. So 0 and 1, and then 0 and -1, which will help us get the new row and new column. So dr plus r and dc plus c. Okay, so if this new r and new c, these two, so if new r is basically greater than equals to 0, or yeah, greater than equals to 0, and this is greater than equals to 0, and new r and new c, new r is less than you can say r, and new c column is less than c, and this pair right here is not in visited, and the value at the grid right now, so grid is equals to, so at this new r and new column is equals to, if you are seeing it as a 0, so you are seeing the water body. That means you have found basically a water body, and you can now say that this, you can keep incrementing the distance from there, so you can still explore from that water body. There might be other water bodies on the next level present. So what you can do is you can append this to, first you can append this to visited set, but before that mark it to, like, append it to your queue. So queue, give it new r and new c, and then you can also mark it visited now. So visit.add, and then add it as pair. And finally, there is one more thing right here. When you are entering to, when you are basically appending it to the queue, your distance now needs to increment. Initially it was 0, but now it needs to increment. I think what we can do is, initially we can keep it -1, because there might be a case where just it does not enter into this, and we want to still return -1, so we'll just mark it return distance. You can keep return distance, and then here, once you're done processing all the node on one level, you can increment your distance. So distance plus 1. All right, I hope you can see the all the code. I can now, by now I can zoom out and here have everything. So we have our queue, and then you're processing everything in the queue at this place, and let me, yeah, we can have all the code in one line. Nice. Oh, this one I was talking about. Okay, so now I guess now we can run it and see if it passes the examples, and it does, and voila. So it's a pretty good solution. Let's clean up a little. Now let's write down the time complexity and space complexity. So time complexity here would be, time complexity is going to be big of, so at most we are visiting actually, like we are appending all the nodes into we are kind of visiting all the nodes in my grid, and the size of the grid is basically n square. So you can definitely say even the BFS is at max going to visit all the nodes. So it's going to be n square that we are already traversing, using this nested for loop. So that also works. And then space complexity is also going to be same, because we are storing all n cross n, this visit set that we are creating. And at max, so visit set is the one that's using the most memory, because we'll keep adding everything to it. All right, there is one more thing. You can get rid of this visited set by actually, rather than adding it here, just flip those values to ones, right? Because if you're seeing the 0, then you can flip it to 1. So next time you don't come across that, and increment the distance, moving on to the next level. So all right, that would be it. Let's mark this problem solved. I'll see you guys later in the next problem.